So we have been talking of state graphs and their implementation using flip-flops and combination logic. One thing which I have not been emphasizing until now is the outputs of state machines. When you say a machine is a machine which is described by a state graph, is a state machine or a circuit basically. It can exist in several states, and it goes from state to state based on a set of based on the present state information, present state, and the input conditions. All that we said, so we were able to draw the state graph based on this information and translate the state graph into a state table, and then get a transition table from which we drew the corner maps and got this combination logic to drive the flip-flops or steer the flip-flops. We called it steering logic. But we never talked about outputs. That is because we took only simple examples of usually counters, either sequential or non-sequential. So counters do not have extra outputs because the states of the flip-flops themselves are the outputs of the counters. But there are circuits in which we will have outputs other than the state outputs, state information. Example is a traffic light controller. It may exist in several states, but then there may be only 3 types of lights. Then certain states make certain lights glow. So there is a need for outputs in addition to the state outputs, and we also mentioned this indicated this in our original drawing of the generalized state machine. If you remember the generalized state machine, so we will say outputs of state graphs, outputs of state machines. So if you remember the generalized state machine block diagram we drew, we said there can be inputs, one or more, called external inputs. Give symbols x1, xn, and then the state information, which are called state variables, which are either present state or the next state. We will call the state variables, or we will say present state and next state. And next state information, which is the stored in flip-flops, the type of flip-flops. Clock, by a system clock. So the outputs of these become the input to the state machine for the next state determination. So if you want to call this ABC, some P, these are the corresponding next state values which are stored here and fed back, and they become the next state, the present state, after the next clock trigger. And in addition, we may have this itself can act as outputs in the case of counters, for example, the state of these flip-flops, that is the counting, the sequence through which the counter goes through, it will act as an output. For example, you want to know the number of counts that has expired, number of counts that has lapsed till now, you can look at the counter states. How many? Suppose you want to count the number of people getting into a room. Anytime the number of people in the room is given by the state of these flip-flops. On the other hand, there are certain conditions, as I said, in the case of a state example of a traffic light controller. In addition to the state, there may be external inputs. These are external outputs, I'm sorry. External outputs, call them Z1, Z2, Zm maybe. M outputs, N inputs, P state variables, which are present state in the next state. When we need P flip-flops in order to store the present state information and next state information, feed it as the next present state for the next clock period. Now, when we are drawing the state graph, we have to accommodate for these outputs, which we have not done as specifically. The state graphs we have drawn so far, the examples we have worked out, we have not specifically taken into account these outputs which can be external outputs. Of course, outputs which are state variables themselves, we don't have to have special provision in the state graph because the state information is anyway there in the state graph, and that information also acts as the output information. But for such outputs which are external to the state graph, I mean external to the state variables, we have not so far made any provision. So what we will do today is to see how to consider this output, how to represent this output, and how to take into account these outputs in our design, overall design. There are two types of outputs possible in a state machine. And based on this, the state machines are classified into two types. One is called the Mealy state graph or Mealy machine. The other is called Moore machine. The Mealy state graph is one in which the outputs are defined for a state and an input condition. What I mean is this: suppose I have a simple machine with three states only. Call this S0, S1, S2. The circuit can exist with one input, external input X, and then if X is 0, circuit remains in this state as 0, X is 1, it goes to S1. In S1, if the X is 1, it remains in the same state, otherwise it goes to S2. Just arbitrarily drawing a state graph. S2, it will go to state S0, whether X is 0 or 1. Just imagine as a simple state graph. Now, if you define an output Z for this system, there will be state variable, two state variables will be there. We have there are three states, so we need a minimum of two state variables. You can call them AB. 2D flip-flops will do. So next set information will be A plus B plus, so forth. But we have not made a provision to show this C, the output, which is different from the state variables A and B, or A plus and B plus. In this, that can be shown in two ways. In a Mealy machine, it is part of the state and the input condition. In a Moore machine, it is part of the state alone. The output is defined for a given state, irrespective of the input condition. In a Moore machine, in a Mealy machine, the output is defined for a given state and an input condition. For example, if this is a Mealy graph, and this machine is a Mealy machine, then I will have to, for each arrow of the input, I should also define an output. So I can say output is 0. The circuit may be in state S0. When the input X is 0, the circuit remains in state 0, S0, output is 0. On the other hand, when it goes from S0 to S1 when X is 1, output may be 0 or may be 1. Again I have to define it. It may be still 0. What I mean is, in S0 this output may be 0 whether the input is 0 or 1. But in both cases you should define it specifically. So I may again put X is Z or Z as 0 here. So that means as long as the circuit is in state S0, this output is 0, Z is 0. But I should specifically say this here and here. For each arrow I should give an output value also. It is in a Mealy machine where the output is defined as a combination or output is defined as dependent on the present state and the input condition. On the other hand, for this one I may have Z is equal to 0 and this I may have 1. Again as an example, I have no circuit in mind. I don't know what it is going to lead to in terms of a realization. And when circuit is S2, whatever is the value of X, it goes to S0. So, but I may say when X is 0, output may be 0. When S is 1, the output may be 1. So in other words, for each arrow, not only I should say what is the input condition which takes the circuit from a given state to the next state, I should also mark the output, one or more outputs. Of course, I have taken a simple example of one output. There is nothing like there should be only one output. In a generalized state machine, there may be several external outputs, Z1, Z2, Z3, M outputs may be there, right? So my state graph will be written such that for a given state, what is the present state, what input condition will take it to the next state, under different input conditions, what are the next states, and what are the outputs for each of those input conditions. So my state graph corresponding to this would be Mealy state, state table. Mealy state table would be present state, input, next state, output. I will have to now give the state variables some labels. So I will call them A and B. I have already indicated A and B here. So it's A, B, 0, 0, 0, 1, 1, 1, or 1, 0 if you want, it does not matter. So the present state value, input X, next state value, output Z. Present state value 0, 0, present state variables, value of present state variables A and B are 0, 0 here. Input X is 0. What will be the next state? Also 0, 0 state. Isn't it? X is 0 leads you back to this state, and output would be 0 for that condition. And when the present state 0, 0, X is 1, circuit is taken to S1, which is 0, 1 state, and the output is still 0. Correct? 0. Take state S1, which is 1, 0, 1 state. This is S0 state. Zero, 1 state. If X is 0, it goes to S2, which is 1, 0, with an output of 1. output is 1 under this state. In state S1, if the input is 0, the output is 1. In state S1, the input is 1, it stays in the same state and the output is 0. Finally, the state is S2, the third state in which circuit can exist. The variable is, the state variables are 1 and 0. In 1, 0, whether or not x is 0 or 1, so I will have to put separately 0, 1. Both times it goes to 0, 0 as the next state. But if the value of x is 0, input is 0, the output is 1, output is 0, input is 1, the output is 1. So I should put a 0 for the output correspond to x is equal to 0 and a 1 for the output correspond to x is equal to 1. This is my S2 state. So this is my state table from which I can draw the transition table based on the type of flip-flop I use. If it's a D flip-flop, it is the same as the transition table. You know all that. And then I need one extra Karnaugh map for output Z. So I can only draw that because you know how to do the maps for A and B. Either it is D flip-flop, in this case you draw the map for A and B, or A plus and B plus in fact. Whereas other flip-flops other than D flip-flops, JK or SR, you have to go through the excitation table, draw the inputs JA, KA, JB, KB, and then draw the Karnaugh maps for each one of those inputs, and then you will do the steering logic. Let us assume you have done all that because you have done it earlier and you know how to do it. For the output only we will draw the map, Z map, output map, map for Z. This is A, B, X. Zero, zero, input 0, output is 0. 0, 0, input 1 is also output 0. 0, 1, input 0, output is 1. 0, 1, input 1, output is 0. 1, 0, 0, output is 0. 1, 0, 1, output is 1. 1, 1 state is not defined, is it not? Next state is not defined because input is not defined. 1, 1 state is not defined, so the next state is not defined. But you have to remember to put the output as zeros, not don't cares. An output don't care can be a 1. And I don't want an output of 1 when you don't need it. When you try to put a 1 and simplify the map, I may land up with a situation where there may be an output when it is not required. Output should be only required, should be generated only when it is required. All other times an output should be 0. So do not use don't care for output conditions, output maps. Output maps, whenever a state is not defined, use as 0. Whenever a state is not defined, make an output of 0, so that if by chance that state happens to, the circuit happens to be in that state because of the transients, when you switch on the power for the first time, the circuit may find itself in that state, and I don't want any output in that state because I don't want a glitch in the output, because that output may be a condition of a lamp, a traffic light, it may be a green light, and I want a green glitch. Suddenly you have a green patch and some fellow will try to pass, then it may cause an accident. Or it could be some other mechanism of aircraft or something which you don't want an unnecessary signal there. So it is always advisable, it's a good design practice, to make all undefined outputs as zeros, not don't cares. And when you put a don't care, you will put as a don't care in the map. When you put it, and sometimes the don't cares will be treated as 1 when you draw the map to simplify it. That may result in a glitch which is not required. Glitch itself is not required. There is nothing like a glitch not required. Glitch. So I will put 0, 0. So my output would be A bar B C X bar or A B bar X. So this will be an additional hardware. So whatever is the steering logic I am going to get for A plus and B plus DA and DB, in addition I need to have one more combinational block or a gate combination to produce output. See. So output has to be taken into account in drawing in specifying the system. When somebody gives you a system, you talk about the various states the circuit is going to be in and where are the input conditions under which the circuit is going to change from state to state. You should also ask what is the output required for each of those states or each of those input conditions, and then specifically mark them in the state graph and carry it on to the state table, onto the transition table, onto the final design. This is called Mealy, as I said. Mealy graph is one in which an output is defined for a state and an input combination. If the output is defined purely for a state and it is independent of the input, the output is same for that state, such a machine is called a Moore machine. So in a Moore machine, if we now modify this into a Moore state machine, I will not write Z's as arrows along with the arrows. I will define Z's inside the state circles, because in a Moore machine output is defined for each state, which is similar to a counter. Now, for example, a counter, we have each state is a count. Counter is a typical example of a Moore machine. But sometimes there may be outputs other than the count. Supposing for all counts less than 5 I want a light to be on. For all the counts more than 5 I want the light to be off. That is an extra output which can only take two values, 0 or 1, depending on the count. So count itself, the state variable itself can be an output, which can also be an output in the case of Mealy machine. But in addition there may be external outputs which are not the same as the state variable, but are dependent on the state variable. Of course, when I say the output is dependent on the state variables, the value of the state variables, the values of the state variables decide the output, of course. But you have to define it in the graph for each state. So since I have a model of X as the input and Z as the output, so Z has to be shown separately in the state graph as well as in the state table, but instead of showing it along with the arrows of the inputs, we will draw it along inside the circles. So now this is how you will find a Moore graph with Z equal to 0. In S0 state the output is 0. In S1 state also output is 0. In S2 state, in S2 state maybe the output is 1. Just arbitrary again. I'm having an output called C, which is 0 here, 0 here, 1 here. That should be reflected. So you can't say it's a state variable, so whatever is the state variable, for example in this case state variable 0, 0 gives an output of 0, 0, 1 gives an output of 0, 1, 0 should give an output of 1. I should indicate that condition in the state graph, also design for it in the output. So now Mealy state graph has been modified into Moore state graph, which is very easy. Moore state table correspond to Moore state graph. Output is now defined for the state. For S0 state the output is 0, whether or not the input is 0, input is present or not. Whether input is 0 or input is 1, the output is 0. That is what we mean by putting the output is within the circle. It is not affected by the arrow. It is not affected by the value of the input x. Similarly, S1 state the output is 0 whether x is equal to 0 or x is equal to 1. So I will have to change this into 0. And for S2 state, in the S2 state output is 1 whether x is equal to 0 or x is equal to 1. Independent of the value of the x, output in state S2 is 1. But it is easier to design this circuit because we know that output is 1 when S2 is for S2 0 otherwise. What is S2? S2 is A B bar. A is equal to 1, B is equal to 0. So you take A B bar and that is the output. And here also in the undefined state of 1 1, even though the state is not defined, the next state is not defined for 1 1, we will still make output 0. As I said, we don't want to have glitches in a state which might come into being because of a false count or because of a transient, because of the power supply being switched on and all that type of thing. We want to make sure that no output occurs at that time when undefined input occurs, undefined state occurs. So my Mealy map, Moore, I'm sorry. There is no need to draw this, but I will do it to complete, for sake of completeness. Which is AB bar. We know it is AB bar because S2 is equal to, when S2, the circuit is in S2, the output is 1. What is the state S2? S2 is A is equal to 1, B is equal to 0, that is AB bar. You can directly write it also from the graph. Sometimes may not be possible because more than one condition under which it can happen, and there will be more than one output. So an input-output condition is also important in the design of a state machine. Outputs are important because outputs need not always be the state outputs. State variables will tell you the state in which the circuit exists at that time, but may not give you the indication of the outputs. The outputs may be independent or different from the state variables. There are two types of outputs possible. One is the Mealy output, where the output is defined in a particular state and an input condition. Output in state S0 when x is 0, when output in S0 when x is 1. On the other hand, an output is defined for the state alone. In state S0 the output is 0, in state S1 the output is 1. If it is defined like that, it is called a Moore machine. In both cases, you should indicate the outputs in the state graph, carry it into the transition table, state table and the transition table, and into the graphs, corner maps, and in the final logic that we design for the hardware. Now, with this background, we will now consider systems. We will have outputs which are other than the state outputs or state variables. We will take some examples. We will start with a simple example of a state graph. So you also know how to draw, because so far I have been assuming state graphs. I never told you how to draw the state graph. Of course, in the state of counters, you know, because if I give you the count sequence, you know how to draw the state graph, because each count sequence is a state. So, put one circle and then put the count value inside and then go to the next count, put an arrow. So, that is one way of doing it, but that is a very simple way. Independently, you should know how to draw a state graph. Suppose I give you specification of the problem. The circuit will have this characteristics, this behavior. This is the type of input, this is the type of outputs, and this is how it should behave. Will you be able to come up with the state graph? That is the first thing. Once you know the state graph, you can implement it. But how do you draw the state graph? You cannot always expect somebody to draw the state graph for you. If you are a system designer, the problem is given to you in word problem, they call it, in a form of a statement. They will tell you what are the inputs and what are the outputs, and what input conditions will lead to what output conditions. Using the statement of the problem, you should draw the state graph, the first thing. Of course, you should ask the question whether you want a Mealy graph or a Moore graph. And then once you have that state graph, then you know rest of the story. State graph to state table to transient table based on the type of flip-flops. And once you have the type of transient table, it's a question of drawing corner maps and drawing a logic for that. So, the exercise is now to start with how to even draw the state graph for a given. So, we will have to do some examples. We will try to take a simple example, see how it works. Suppose I want to detect a pattern. Suppose I am seeing whether data is coming in serially, one bit at a time. And when a particular pattern occurs, I want to know that. That could be a password. You may send a bit stream, and embedded in the bit stream may be a pattern you are looking for. When that pattern comes, you know that you have identified the correct sender or recipient, and then from then on you can start and do whatever you want to do with that. So, a simple a pattern detector could be so I am going to assume that we are having a single input X and a single output C. I don't know the number of states now because I need to draw the state graph. Only if I draw the state graph, I know how many states are there, and then only I know how many state variables will be there. But I know it is a state machine because the input is coming one at a time, one bit at a time. It's a clocked input. So I know there is a clock here. So the input occurs like this. For each clock pulse, the input may be like this. We don't know what way it is going to come. Let us simply say whenever a state 0, 1, a pattern 0, 1, 0 in this sequence occurs. Supposing a sequence 0, 1, 0 occurs, I should know it, and then indicate it by an output high. Rest of the time output is 0. So, output will be 0 normally, but when a pattern of 0, 1, 0 is detected by this circuit that we are designing, for one clock period coinciding with the third 0, the output should be 1. And then again the output will go back to 0, right? So, my output will be 0, 0, 0, 0. I don't know, I have not even put 1. I should probably try to put 1 0 here, otherwise we are never going to get it. Okay. 0. Now 0, 1, 0, this is the pattern I am looking for, which has been identified. And I said along with the third bit of the input pattern is the time. So the first 0 comes, then a 1 comes, then a 0 comes. Along with the third bit of the input, I want an output 1. As long as the third bit of the input exists, output will be 1, and then when the next bit comes, the output has to fall back to 0. So along with this, there should be an output of 1. This is only a typical sequence, it is not the sequence. I may get the sequence in any order, I may get zeros and ones in any pattern, but wherever there is an embedded 0, 1, 0, I should be able to detect it. The circuit should be general. This is only an example sequence, not the specification. So for example, an input sequence may be like this, for which I need an output sequence like this. This is the sequence to be detected, or pattern to be detected. Now again 101. Now the question is, after 101 what happens? Again should it reset, or if I take this 0, 1, 0 as one output and then there is a 0, 1, 0, so there is one more 0, 1, 0 here. Whether this pattern also is considered as another pattern, or is it because it is overlapping with the previous pattern, should it? That also you should decide. See, all these are very clear in the specification. You can't just jump to the design board or the breadboard as soon as somebody tells you a problem. If the problem is vague, you should ask questions. Everything should be clear. Should it be a mealy machine or a Moore machine? Do you want? Do you want a pattern, overlapping pattern also should be detected, or only clear patterns should be detected? All those questions you should ask beforehand, because your circuit will be vague otherwise, and because you should always understand what the person wants before you can go and design the circuit. So let us now assume overlapping pattern also should be detected. Whenever there is a 0, 1, 0, whether or not a separate pattern, even if it is a part of another detected pattern 101, I should still be able to detect it. If that is the answer, then I should put a 1 here again. And there may be any number of 0, 1, 0s. Wherever there is a 0, 1, 0, whether as an independent pattern or an overlapping pattern, corresponding to the third 0 of that 0, 1, 0, I need an output 1 for 1 clock period. That is the problem statement and an example sequence, sample sequence, input and output. Now with this I should go to the drawing board and then draw the state graph. How do I do that? The circuit has to exist in a state. We have to assume that the circuit is existing in a state, and then the input comes, and then whether it looks at as a 0. If it is 0, how does it treat it? If it is a 1, how does it treat it? And all that. So the next step is to draw the state graph for this. And let us also put a mealy machine to start with. So these are my input specifications. This is the pattern detector, one input and one output with a clock. Pattern to be detected is this, and I want it as a mealy machine, and I want overlapping patterns also to be detected. With this I go to the next step of the state graph drawing. I may not draw the best state graph, but I should start somewhere now. I have to get going. So the state graph for this problem, any design problem will have more than one solution, and one of them may be better than the other, an optimum solution and all that. We don't worry about whether what I will do is the best solution possible, at least to start with. Later on we should improve and then probably give the best possible solution. So let us say the circuit exists in a state called S0. It's a mealy machine, so there is no output within the state. And this S0 is a state in which the circuit normally exists, so it will say reset state. When the circuit starts, the power starts, power up. When you power up the circuit goes to S0 state. Let's assume that. You have to start somewhere. And then the input comes. Input can be, only one bit is coming at a time. So input is X. The input can be either a 0 or a 1. If it is 0, I should be careful because it could be part of a 0, 1, 0. So 1 I have no use for it, discard it, right. So what I will say is, if it 1 occurs, the circuit can remain the same state as reset state. It doesn't matter to me whether it's a 1 occurs and a number of 1s occurs. Any number of 1s occurring has no meaning because the pattern has not started. And it can continue to be in S0 state, and no output is also required. So this is the way to put this. Usually they put X stroke C. The input and the corresponding output is written. Instead of putting X is equal to 0 is equal to 0, this is the normal way of representing this in a state graph. In books, in textbooks, you will see a value, binary value with a slash and another binary value. The first binary value is the input value, second binary value is the output. This is a convention. So first is the input, second is the output. On the other hand, if X is 1, I mean 0, I will have to be careful because it could be part of a 0, 1, 0, right? So I am going to remember this state as a state in which 0 has already occurred. This is a little notes I am keeping. And even now the output is 0 because output will be 1 only when 0, 1, 0 is. So first 0 is not going to give you any output. But I am sure in a state where I have detected a 1, I have detected a 0. So to that extent I have proceeded, progressed. In S1 again, as next bit comes, it could be a 0 or a 1. If it is a 1, we are going back to square 1. If it is a 1, it is, 0, I am sorry, 0, 1. 0, 1 is a part of a sequence. If a 0 occurs in this, any number of zeros has no meaning, only when the last 0 is of interest to us. 0, 0, 0, 0. I have already detected the first 0, a second 0 has no meaning because if the latest 0 will be stored and rest of the zeros will be discarded. So if a 0 occurs, I will continue to be in same state with same output. Whereas a 1 occurs, this could be the 0, 1 of the 0, 1, 0, right? So I will have to go to a new state called S2. 1 is the input. Again, still the output is still 0 because 0, 1 itself cannot give you the output. Only 0, 1, 0 can give you the output. So 1 is a new state, all right, but output is still 0. So S2 state would be a state in which 0, 1 will be remembered. Now in S2 again a third bit can be a 0 or a 1. The third bit is a 0. You have got the 0, 1, 0 pattern completed, so out should be 1. But where should I go? I should go to S1 which stores the first 0 because this 0 could be the starting of a next pattern. So when at this time when S is 0, I will go here, X is 0, but it will give an output of 1 because I have completed a 1, 0, 1. Output will be 1 because I have completed a 1, 0, 1, and it will go back to S1 because S1 is going to remember the latest 0, and this latest 0 will be could be the start of the next pattern, as in this case. On the other hand, if S2 happens to be a 1, if it's a 1 there is no point because 0, 1, 1 has no meaning. I have to start all over again. I can as well go to the reset state without any output. This is state graph. You see, it works. It may not be the best state graph. It may be possible to do it simpler. Later on we will see whether there is any way of, like corner map reduction, like Boolean algebra. You try to simplify and finally you will end up with something. It may or may not know whether it is right. Then you go for corner maps. Similarly, the state graph also there are some techniques to see whether this is the best possible state graph, the minimum possible state graph. We may or may not have time to do that, but that doesn't matter. We are only starting to design our own circuits. We are now able to translate a word statement into a state graph and then into a corner map into a hardware diagram, which hopefully when you are given those parts, components and a breadboard, you will be able to wire it up and even make it work, which is what will go into a lab next semester. So the idea is from somebody's description of the problem to the statement of the final realization of the circuit has to go through all the stages, and this is the most critical stage, because understanding the problem translated into a graph. From here on it is a routine procedure, from state graph to state table, and state table to transition table to corner map to gates, gate to buying them and then putting in the breadboard and testing it. It's all routine. No? The most critical part of this design is to understand the specs and translate it into a workable state graph. So this is the state graph. From here you know how to proceed, because you know from here you have to assign states. For example, I can say S0 is equal to 0, 0, AB are the state variables, 0, 1, S2, 1, 0, and then we can go to state table, and then I can use D flip-flops, or I can use JK flip-flops, and I know how to draw the transition table, how to draw the corner maps, how to get the output map, how to put them together and show it as a drawing in a design board on a design sheet, and then how to translate it into hardware when you get those components. But this is the thing, the state graph formation. The circuit can exist in 3 states. In the first state it is waiting for the state, for the bit to come. The bit can be 1 or 0. If it is a 1, there is no use for it. So 0, it goes and remembers that. It is a 0 there, again the same 0 has to be remembered, so there is no need to go to new state. It continues to be in the same state. So 1 comes, go to another state where it remembers 0, 1. In this, if a 0 comes, you have completed the pattern, but remember the last 0. On the other hand, if a 1 comes, there is no use for any of them, because you know 0, 1, 1 has no meaning, because again you have to start all over again. You have to go here. And no output except in this case when 0, 1, 0 is completed. All other states the output is 0. And I want to take it as an assignment to complete this state graph into hardware design. Taking it from this assignment, take this assignment and draw the state table and use JK flip-flops and get a transition table and draw the logic diagram for the steering logic for the flip-flops as well as the output. See, we will see more examples in the next classes.